The objective of this presentation is to discuss the various strategies that can be adopted to separate the isomers of hexane: normal hexane, 2-methylpentane, 3-methylpentane, 2,2-dimethylbutane, and 2,3-dimethylbutane. Let's have a look at the properties of the hexane isomers. Firstly, let's look at the research octane number. We see that the research octane number increases as we proceed from the linear normal hexane to the monobranched isomers and the dibranched isomers. The dibranched isomers have the highest octane numbers, and these dibranched isomers are the preferred components in high octane gasoline. And therefore there is a need to separate the mixtures of hexane isomers in order to recover components that have the higher octane number so that they could be incorporated into the gasoline pool. The boiling points of the hexane isomers are tabulated here. We see that the normal hexane molecule has the highest boiling point, and it is possible to separate the normal hexane from the branched isomers by distillation. And in industrial practice, this occurs in distillation columns that are termed dehexanizers. However, the separation of the dibranched for the monobranched isomers is more difficult because the boiling point differences are significantly lower. And the objective of this presentation is to consider separations of hexane isomers using adsorbents. The simplest approach that can be adopted to separate hexane isomers is to exploit the principle of molecular sieving. If we use an adsorbent such as LTA5A zeolite, LTA stands for Linde type A, and LTA5A zeolite contains 32 sodium cations per unit cell and 32 calcium cations per unit cell. The LTA structure consists of cages separated by windows that have dimensions of about 4 angstrom to about 4.6 angstrom. It is possible for a linear molecule such as hexane to diffuse easily or relatively easily through the 8-ring windows of LTA4A zeolite, whereas the monobranched isomer and the dibranched isomers are limited in their ability to hop from one cage to the adjacent cage because the dimensions of the molecules prevent the intercage hopping. And therefore, in principle, it is possible to separate the normal hexane from the branched isomers using LTA5A zeolite. The processing scheme currently used in industrial practice is shown on this slide. Consists of a feed mixture that is isomerized in a reactor with modernite catalyst to produce a product containing the isomers of hexane, and this mixture is sent to an adsorption unit containing 5A adsorbent that allows selective uptake only of the normal hexane isomer because of configurational considerations. The mono and the di-branched isomers are prevented from entering inside the pores of 5A zeolite. The rejected components consisting of monobranched and di-branched isomers can be incorporated into the gasoline pool, and the normal hexane can be recycled back to the isomerization reactor. The preferred processing scheme, however, is to select an adsorbent that separates the linear and the monobranched isomers from the di-branched isomers, so that the di-branched isomers with the higher research octane number can be incorporated into the gasoline pool, and the linear and the monobranched isomers can be recycled back to the isomerization reactor. The question is, which adsorbent should be used to effect this separation of the mono-branched and the linear from the di-branched? One candidate adsorbent that is capable of separating the linear and branched isomers from the di-branched isomers of hexane is Fe2BDP3, that has triangular channels of 4.9 angstrom size. The details of this metal organic framework are provided in this article. The isosteric heats of adsorption of the hexane isomers in the 4.9 angstrom triangular channels of Fe2BDP3 are shown in this graph here. The hierarchy of binding strengths is normal hexane, 2-methylpentane, 3-methylpentane, and the di-branched isomers 2,2-dimethylbutane and 2,3-dimethylbutane. The linear hexane molecule can align itself along the vertices of the triangular channels, which each of the carbon atoms effectively interacting with the channel walls. The van der Waals interaction of the more compact monobranched and di-branched isomers are lower in strength than that of the linear isomer. Breakthrough experiments show that the hierarchy of breakthroughs follows the hierarchy of binding strengths. The di-branched isomers are the first components to break through, followed by 3-methylpentane and 2-methylpentane, and finally the linear hexane molecule breaks through the fixed bed adsorber. Therefore, Fe2BDP3 can be used as adsorbent in a PSA scheme shown in the previous slide, wherein the first two components that are rejected into the gas phase can be removed and incorporated into the gasoline pool, and the adsorbed components can be desorbed and recycled back to the isomerization reactor. Let's consider the traffic of linear hexane and monobranched isomers 2-methylpentane and 3-methylpentane as it moves within the triangular channels of Fe2BDP3. The mobility of the linear hexane molecule is higher than the mobility of the monobranched isomers, because the monobranched isomers are more strongly confined within the 4.9 angstrom channels, whereas the linear isomer is less strongly confined. A special feature of hexane separation with this morph is that adsorption and diffusion proceed hand in hand, because hexane, which has the highest adsorption strength, also has the highest diffusivity value, and this combination of adsorption and diffusion being synergistic is useful in fixed bed separations. The di-branched isomers 2,2-dimethylbutane and 2,3-dimethylbutane have compact configurations and are very strongly confined within the triangular channels. Their diffusivities are even lower than those of the monobranched isomers. The combination of poor adsorption strengths and low diffusivity values makes for earlier breakthroughs in fixed bed adsorbers, and this is desirable from a process standpoint, making Fe2BDP3 a viable candidate for commercial use. Molecular simulations have established that cobalt BDP that has 10 angstrom size square channels is capable of separating the isomers of pentane and the isomers of hexane, relying on differences in the van der Waals interactions between the alkane isomers and the pore walls. Let us try to obtain a feel for the motion of pentane isomers, normal pentane, 2-methylpentane, and neopentane within the channels of cobalt BDP. The channel dimensions of 10 angstrom are larger than those for Fe2BDP3, and therefore the differences in the diffusivities between the pentane isomers is minimal. These animations show the motion of normal hexane, 2-methylpentane, and 3-methylpentane within the square channels of cobalt BDP. The diffusivities of these isomers are nearly the same, and the separations are largely based on differences in the van der Waals interactions of the alkane isomers with the pore wall. Here we look at the animations for the motion of 2,2-dimethylbutane and 2,3-dimethylbutane in cobalt BDP. The diffusivities of these di-branched isomers are nearly the same as for the linear and monobranch isomers, and the separations of hexane isomers is purely on the basis of van der Waals interaction. Indeed, this is confirmed by molecular simulations for a 5-component mixture of hexane isomers. We see that the component loadings in cobalt BDP follow the hierarchy normal hexane, 2-methylpentane, 3-methylpentane, 2,3-dimethylbutane, and 2,2-dimethylbutane. This allows the use of cobalt BDP as an adsorbent in the PSA scheme for octane upgrading. Let us examine the use of mortonite for separation of hexane isomers. Mortonite consists of 1D channels that are 7 angstrom in this direction and 6.5 angstrom in this direction. The 1D channels are connected to side pockets that have dimensions 4.8 and 3.4. The side pockets are unable to locate the hexane isomers. The hexane isomers are normally to be found along the straight 1D channels. And let's have a look at the animations for normal hexane conformations and 2,2-dimethylbutane. You will note that 2,2-dimethylbutane has a smaller footprint, and therefore at saturation it is possible to locate more of the 2,2-dimethylbutane within the 1D channels than normal hexane that has a longer footprint. In principle, it is possible, therefore, to separate the isomers of hexane exploiting on the entropy effects due to differences in the molecular footprints. By sampling several thousand conformations of each of the hexane isomers, it is possible to construct a probability distribution of the lengths of the footprints for normal hexane, 2-methylpentane, and 2,2-dimethylbutane. 2,2-dimethylbutane has the shortest footprint, say about 2.8 angstrom. 2-methylpentane has a footprint on average of 4.5 angstrom, and the normal hexane footprint on average is larger, which is about 5.5. Molecular simulations of the unary isotherms are shown here for normal hexane, 2-methylpentane, and 2,2-dimethylbutane, and you will note that at saturation the loading of 2,2-dimethylbutane is higher than that of 2-methylpentane, and the loading of 2-methylpentane is higher than that of normal hexane. The saturation loadings are the inverse of the footprints of the corresponding isomers. The differences in the footprints of the hexane isomers can be exploited to realize separations based on the differences in the footprints. To demonstrate that, we carried out configurational bias Monte Carlo simulations for a binary mixture of normal hexane and 2,2-dimethylbutane in mordanite at a temperature of 433 Kelvin. The component loadings are plotted against the total fugacity in the bulk fluid mixture, which is maintained equimolar. That means the partial fugacity of normal hexane is the same as that for 2,2-dimethylbutane in the bulk fluid mixture. The component loadings are plotted here against the total fugacity in the bulk fluid phase, and we see that up to a total fugacity of 2 times 10 to the 4 pascals, the component loadings are practically identical. But as the pore occupancy increases with increasing fugacity, the mixture adsorption becomes increasingly in favor of the dibranched isomer at the expense of the linear isomer. Now, the dibranched isomer has the shortest footprint and therefore can pack more efficiently within the channels. So the reason that mixture adsorption favors the dibranched isomer is ascribable to entropy effects that favor the component that has the higher packing efficiency. Further explanation of entropic separations is provided in my presentation that is on my YouTube channel. See also the paper that is referenced here. Hexane isomers can be separated using MFI zeolite by exploiting a different type of entropy effect. To illustrate this, let us consider the unary isotherm of normal hexane. Now, MFI zeolite consists of a set of straight channels and zigzag channels. The dimensions of 5.5 angstrom. Normal hexane is a linear molecule that can align along either the straight channels or the zigzag channels. This is the XZ view, looking at it from the top, and indeed they are zigzag in shape. They're also called sinusoidal channels. The length of a normal hexane molecule is commensurate with the distance between channel intersections. Per unit cell of MFI zeolite, there are 4 intersection points and a total of 8 normal hexane molecules can be accommodated within the MFI framework at saturation conditions. Monte Carlo simulations of the unary isotherm for 2-methylpentane in MFI zeolite are shown here. In contrast to normal hexane, a maximum of only 4 molecules per unit cell can be accommodated within the MFI framework at post-saturation conditions. This is because of the configurational penalty that is experienced by 2-methylpentane. It requires more legroom and it prefers to locate at the channel intersections, and an extra push is required to locate these 2MP molecules within the straight or zigzag channels, and therefore up to a pressure of 10 to the 4 pascals, the intersection sites are the preferred locations for 2-methylpentane. Configurational bias Monte Carlo simulations were conducted for binary mixtures of normal hexane and 2-methylpentane. The bulk fluid mixture is equimolar. In other words, the partial fugacity of normal hexane is maintained the same as the partial fugacity of 2-methylpentane. The component loadings in the adsorb phase are plotted here. The red circles denote the loadings of normal hexane, and the green squares denote the loadings of 2-methylpentane. We see that up to a total fugacity of 1 pascal, the component loadings are almost identical to each other. However, as the total fugacity increases beyond this value of 1 pascal, the mixture adsorption gets increasingly in favor of the normal hexane molecule that packs more efficiently within the intersecting channel structure of MFI zeolite. On the other hand, 2-methylpentane that is configurationally challenged reduces to a value of nearly zero in its component loadings. In other words, as the structure gets increasingly occupied, the normal hexane molecule is preferentially adsorbed at the expense of 2-methylpentane. That is virtually excluded because it is entropically challenged. This entropy effect is so strong that it leads to near total exclusion of the branched isomer. Further details are provided in these publications.